Welcome to module 2 of the unit Determinants and Matrices, and in this module we'll go through some types of matrices. Okay, recall that in the previous module we have defined a matrix, which is a rectangular arrangement of numbers in rows and columns, and then we have talked about some properties or how elements of the matrices are represented by a unique position assigned to it depending on the number of row and column it appears in the matrix. Now some of the types of matrices that we usually come across. Okay, we have row and column matrix. Okay, a row matrix is a matrix having only one row. So this here, like matrix A here, has only one row, row 1, and it has 3 columns. Okay, so the dimension of this matrix is 1 by 3. Okay, so it has one row. Matrix B also here has one row. It is 1 by 2 matrix, one row and 2 columns. So a matrix which has only one row is called as a row matrix. The same way here, matrix C here. Okay, it has one row, 1, 2, 3, 4, 5 columns. So it is 1 by 5. So it has only one row. It is called as a row matrix. The same way, a column matrix is a matrix having only one column. Okay, so it will be just like the opposite way, like here. Okay, so I have only one column here, and I have 1, 2, 3 rows. So it is like a 3 by 1 matrix. The same way here, matrix Y has only one column, 1, 2, 3, 4 rows. So it is 4 by 1. So the number of columns here is 1. So it is called as a column matrix. A square matrix, okay, as the name suggests, a matrix in which the number of rows and columns is the same. Okay, say for example, here matrix A, the number of rows is 2, number of columns is also 2. It is a 2 by 2 matrix, or the number of rows and number of columns is the same. So it is, we say, is a square matrix. The same here, matrix B. It has 1, 2, 3 rows, 1, 2, 3 columns. It is a 3 by 3 matrix and a square matrix. The same way here, matrix C. Okay, it is 1, 2, 3, 4 rows and 1, 2, 3, 4 columns, a 4 by 4 matrix. Number of rows and number of columns is the same. So it is a square matrix. In a square matrix, the elements A, I, J, where I is equal to J, are called as diagonal elements. Okay, so wherever the positions here, the number of row and the column it appears is the same, they are called as diagonal elements. So precisely in this matrix, these are the diagonal elements. 1, 1 is the position. The position of this is 2, 2. The same way here, the diagonal elements are this 3, -2 and 0. What happens in these positions is, here the number of row and the column in which the number appears is the same. I is equal to J. This is 1, 1. This is 2, 2. This is 3, 3. Okay. So I is a row and J is the column. They are both same. The same way here, the diagonal elements is this are 3, 6, 1 and 1. This is 1, 1. This is 2, 2. This is 3, 3, and this is 4, 4. The elements which are not in the diagonal are called as non-diagonal elements. So these are the elements wherein the row and the column in which they appear are not the same. I is not equal to J. Okay, so all these are non-diagonal elements. These are all non-diagonal elements. Here the non-diagonal elements are 0 and 0. Here the non-diagonal elements are this and this. Okay, so we define a diagonal matrix. A square matrix in which every non-diagonal element is 0. Okay, so for example, you consider this matrix A here. Okay, the diagonal elements are this, right? And the non-diagonal elements are this here, 0 and 0. So a square matrix, and it's a square matrix, it is a 2 by 2 matrix. A square matrix in which every non-diagonal element is 0. So non-diagonal elements are here 0. So this is a diagonal matrix. The same way here, a matrix B, which is a 3 by 3 matrix. Okay. So here the diagonal elements are this, and all the non-diagonal elements which are this are zeros. So this is a diagonal matrix. The same way consider the matrix C, which is a 4 by 4 matrix as a square matrix. Okay, so these are the diagonal elements, and all the non-diagonal elements, these are the non-diagonal elements, they are all 0. So this is called a diagonal matrix. Then a scalar matrix. A square matrix having non-diagonal elements as 0 and all the diagonal elements are equal. Okay, so this is similar to what we have done in the diagonal matrix, except that now all the diagonal elements are equal. Okay, like this. So non-diagonal elements are 0 and all the diagonal elements are same. So this is a square matrix 2 by 2 satisfying that condition. So this is, we say, is a scalar matrix. Here also this is a 3 by 3 matrix. Okay. All the diagonal elements are equal, that is 3, and non-diagonal elements is 0. Okay, so you can also say that this is a diagonal matrix with all the diagonal elements same, and that we say is a scalar matrix. The same way here, this is a 4 by 4 square matrix. All the diagonal elements are same and all the non-diagonal elements are zeros. So a scalar matrix of order 4. Then a zero matrix, as the name suggests, a matrix having every element as 0. Okay, this is a 1 by 3 zero matrix, the matrix A. This is a 2 by 2 zero matrix, all the elements in the matrix are 0. This is a 2 by 3 zero matrix, 2 rows and 3 columns. This is a 3 by 3 zero matrix. Then we have unit or identity matrix. Okay, we mostly refer to it as identity matrix. A square matrix having every non-singular element equal to 0. No, this is non-diagonal. A square matrix having every non-diagonal element equal to 0 and every diagonal element is equal to 1. Okay, so something like this. So square matrix, so it's a 2 by 2 matrix. Every diagonal element is 1 and non-diagonal elements are 0. Okay, this is basically a scalar matrix, okay, with all the diagonal elements as 1. The same way this we say is a 3 by 3 identity matrix. So this is a 2 by 2 identity matrix, okay, and this is something that we are going to use very often in the future modules. This is a 3 by 3 identity matrix, okay, all diagonal elements 1 and non-diagonal elements 0. Then here we have a 4 by 4 identity matrix. Okay, so all diagonal elements 1 and non-diagonal elements 0. This identity matrix is the same as like how you have a number 1 in a number system. Okay, and it will possess the same properties. Properties are satisfied by 1, the number 1 in the usual number system. Then we have upper and lower triangular matrix. Okay, an upper triangular matrix is a square matrix in which all the elements below the diagonal are 0. Okay, let's say for example here. Okay, if you look at matrix A, okay, all the elements below the diagonal, so diagonal is here and below the diagonal are this, so it is 0. The same way here, look at matrix B, it's a square matrix again, it's a 3 by 3 matrix, diagonal is this and the elements below the diagonal are here, they are all 0. Okay, so we say this is an upper triangular matrix. So when it's upper triangular matrix, you have at least a non-zero element here in upper triangular, and all the values in the lower triangular, the lower triangle or the elements below the diagonal are 0. Now this is a 4 by 4 upper triangular matrix. Okay, diagonal is here and all the values below the diagonal are 0. The same way we have a lower triangular matrix, it will be just be the opposite. A square matrix in which all the elements above the diagonal are 0. This is just the other way around now. Okay, so matrix A, it's a 2 by 2 matrix, diagonal is here, and now the elements on top above that diagonal are 0. Then it's called as lower triangular matrix. The same way, here I have matrix B, which is a 3 by 3 matrix, and all the elements above the triangle are 0, so it's called as a lower triangular matrix. The same way, I have a 4 by 4 lower triangular matrix here. In lower triangular matrix, the values above the diagonal are 0. Then we have something called as the transpose of a matrix. Okay. For a matrix A, the matrix obtained by interchanging the rows and columns of A is called as the transpose of A, and the transpose of A is denoted by A dash, A bar, or A with a subscript T. Let's say, for example, suppose I have a matrix A like this. If I have to find out the transpose of this, we'll say A transpose. What we have to do is interchange the rows and columns. That means the first row will become the first column here. So this 1 minus 3 2, I have to write 1 minus 3 2 like this. Row becomes column. The second row becomes the second column, 0 4 minus 1. So if here the dimension of the matrix A was 2 by 3. So when we write down its transpose, the dimension is going to be the opposite, 3 by 2. So rows become columns or columns becomes rows. We interchange rows and columns. So if you suppose you consider this matrix B. Okay, now this is a 3 by 3 matrix. So if I want to write down the B transpose or B dash, then I have to interchange rows and columns. So the first row becomes the first column. So 1, 2, 3 like this. So this 1, 2, 3 goes into the column. 4, 5, 6, the second row, 4, 5, 6 like this. And then 7, 8, 9, that is the row will become column here. Of course, here the rows and columns are the same. So this will again be a 3 by 3 matrix. So this is the transpose of the matrix B. The same way if I consider matrix C. Now this is a matrix of order 3 by 4. So if I have to write down the transpose of this, okay, what will be the order of the transpose? It will be 4 by 3. So the first row becomes the first column. So it will be 5 0 1 3 here. So it will be 5 0 1 3. 9 4 8 8 will be here, 9 4 8 8, and 8 minus 4 2 2, that row will become a column here, and the order of this is 1 2 3 4 rows and 3 columns. So given a matrix, this is how we write down its transpose.